Welcome to Lecture 5 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we'll continue developing the tools we need to analyse the consumer's problem, and we'll be looking at utility functions, marginal rate of substitution, and looking at the budget constraint and what this means. This will come together in the next lecture so that we can actually look at solving the consumer's problem and analysing the properties of the solution. But today we're mainly developing the tools that we need. Let's start with a quick recap of what we did last time. In the last lecture, we modelled a consumer's preferences over bundles of goods, which we denoted A, B. We had two goods, goods 1 and 2, which we assumed were perfectly divisible, so the consumer could have any quantity of these goods, and homogeneous in the sense that one unit of good 1 is the same as any other unit of good 1, and one unit of good 2 is the same as any other unit of good 2. Consumer had preferences over these bundles of goods, and we made some restrictions about these preferences. We wanted them to be as general as possible to allow for different types of people, but we insisted that certain rules or axioms were obeyed. So we said preferences are rational if they satisfy the axioms of completeness and transitivity. We also assumed the axiom of monotonicity, which was the requirement that more is better. So the consumer preferred bundles of goods which had greater quantities of each of the goods. After defining preferences, we developed a tool called Indifference Curves, which is a way of graphically representing the consumer's preferences. So we can draw diagrams to represent the consumer's tastes, and we called a set of indifference curves a preference map, which we drew in commodity space. After defining indifference curves and the axioms of rational choice, we showed that indifference curves inherit several properties. Most notably, we proved that indifference curves are thin, they slope downwards, and they don't intersect. So if any of this feels unfamiliar, it may be worth going back over some of that lecture to make sure you're fully satisfied with each of these properties of indifference curves, which we will continue to use as we progress today. So let's talk about the idea of utility functions. Now, this far we've been working with preferences. So, for instance, we might imagine that we meet a rational decision maker who expresses the following preferences over bundles. Let's suppose that our decision maker strictly prefers bundle A to bundle B, and he's indifferent between bundle B and C, and he likes C better than D. So he's put them all in order, he's able to compare everything, which is our basic requirement for rationality. Now, we could actually do economics just using preferences, but we don't know a lot about these things, really. We've never encountered them before. But what do we know a lot about? Well, anyone who's had as much mathematical training in your background as you have knows a lot about numbers. You know about solving equations, you know about functions and differentiation. You'll be learning about constrained optimization and linear algebra, all sorts of techniques, all in the world of numbers. So the idea of a utility function is simply a way of translating this information, okay, what we know about preferences, into something involving numbers. Now, it's something we construct. It's an artificial concept. So let me show you by example. Suppose I'm going to assign numbers. Okay. Let's assign some numbers to these bundles, and I'll call these utility of A, and let's just pick a number. Let's call this, let's call that 4. And let's suppose I choose the utility of B to be 2. And let's suppose I choose the utility of C to be. Well, what would that need to be? It's if I'm indifferent, I'll just put that the same as utility of B. We'll talk about that in a second. And I'll let the utility of D equal a smaller number still, let's say 1. Okay. Now I've just plucked these numbers essentially out of thin air, but I've done one important thing. What I've made sure is that the utility of A, which is 4, is bigger than the utility of B, which I chose to be 2. I could have chosen 3.9, or I could have chosen 2.75. Any number, as long as it was smaller than 4, this inequality would still be true. Okay? And I've chosen that to be the same as the utility of C. And then the utility of D, I just chose the number 1, which is smaller than, so 2 is greater than the utility of D, which we chose to be equal to 1. But we could have chosen any number as long as this inequality still was true. So hopefully you can see the idea there. Essentially, I'm just choosing numbers. Here I've chosen 4, 2, and 1, so that these the numbers are ordered in the same way as the individual's preferences. Okay? So in a sense, this utility function now, this function u, it's a function because I plug something into it and out pops a number. I plug a bundle A, B, C, or D into it and out pops a number. It's a function, and we say it represents. So let's say u, and an important word, so I'll write it in capitals, represents our decision maker's preferences. Okay? And it represents in the following sense. Our decision maker prefers one bundle A to another bundle B if and only if, so I can draw this arrow in 2 directions, the number that we assigned to A is at least as large as the number that we assigned to B. Okay, so that's the basic definition of a utility representation. The important thing to realize here is that really we're just inventing this concept utility as a way of translating something we're interested in, preferences, but perhaps we don't know a lot about, into something that we do know a lot about, numbers. Now we're in the world of numbers. We can open our mathematics textbooks and use all sorts of amazing tools that are available to us. So let's talk about the idea that utility is ordinal in this case. So if we remember, we began with preferences. A preferred to B. Our individual was indifferent between B and C, and he preferred C to D. And then we came up with some numbers. The utility of A was greater than the utility of B, equal to the utility of C, greater than the utility of D. And we just had to come up with some numbers so that these preferences were appropriately represented by the numbers we chose. Now we chose the utility of A equal to 4, the utility of B and C equal to, do we choose 2 or 3? Which let's say 2. Yep, we chose 2. And the utility of D equal to 1. Now, the important thing about these numbers was that they put the bundles in the right order to represent these preferences. That's the only thing that was important about these numbers. So, for instance, I could have chosen... so let's imagine that I square all of these numbers. Okay, so I'm going to define a new function v, okay, so that, let's say that v of, if I take a bundle here, it's just the utility of A squared, okay, and we're going to assume that the utility of A is positive. Okay, so we have positive numbers. Now let's imagine squaring all of these numbers so that v of a, this different function, would give 16, v of b would be 4, and v of d would equal 1. Okay. Now notice with this new function that v of a is greater than v of b, which is equal to v of c, which is greater than v of d. Okay. So this function v also puts all of the bundles in the appropriate order. Okay, so this is another utility representation. Okay, so that's the important thing. Utility representations are not unique. There's nothing special about the numbers apart from the fact that they put the bundles in an order which represents the particular consumer's preferences. Okay, so one way of making this formal is to denote the idea of, let's say, a function f, and let's say it's strictly increasing. Apologies, strictly increasing. If, what does that mean? Means that if x is larger than y, then f of x is larger than f of y. Okay? So that's the idea of a strictly increasing function. So we can formalize this idea. So here, the squared function for positive numbers. In the positive domain, it's strictly increasing. Okay? So if we take any u, so if u represents preferences, okay, and we know what that means. The utility of one bundle, according to this function, is larger than another bundle, according to this function, if and only if the consumer prefers that bundle. Okay, so if u, kind of the numbers that this utility function u generates, put bundles in the correct order according to these preferences, okay, then I could say let v, which is f of u, represents preferences, ... provided, or if and only if, the function f here is a strictly increasing function. Okay, so when I take utility, these numbers, and I perform some operation on them, as long as that transformation is strictly increasing, everything will still be in the right order, and v will indeed be another utility function. Okay, so there's an infinite number of utility functions. As soon as we've found one, we can generate many, 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 many more. Okay, so there's nothing important in particular about the numbers 4, 2, and 1. Okay, if, for instance, the fact that 4 minus 2 equals 2 and 2 minus 1 equals 1 is kind of meaningless here. 16 minus 4 is 12 and 4 minus 1 is 3. So them differences don't seem to mean anything. But the fact that 16 is larger than 4 means something. The fact that 4 is larger than 1 means something. And that's the only conclusion we can use from these numbers. Sometimes we call this ordinal utility. Okay, which you can see has the word has the prefix which sounds like order. The only thing that matters is the order. Now that we have the idea of utility, now if we were to draw a diagram of this, it would be a three-dimensional diagram such as the one on the screen here, because we have two goods being turned into one number. Two goods form a bundle, and that bundle generates a utility number. Okay? Now, an indifference curve, if you remember, we defined as I of A, so the indifference curve associated with A, is equal to a set B, which satisfies, so it's the set of all the different bundles B, which satisfy the rule the consumer is indifferent between A and B. Okay, so that's how we described an indifference curve using set builder notation. Now, using utility notation, we could simply write this as the indifference curve associated with A is equal to the set of all bundles B that satisfy the rule the utility of A is equal to the utility of B. Okay, because having equal utility is equivalent to the consumer being indifferent if this utility function represents preferences. In this sense, we can see the indifference curves in this three-dimensional diagram here as the level sets or the level contours of this utility function. So that's the connection between indifference curves and this kind of three-dimensional drawing of a utility function. Drawing three-dimensional diagrams is incredibly difficult, and it's not something we will typically do. So typically we will just draw a preference map in commodity space, and perhaps we might label indifference curves by saying this is the indifference curve associated with this particular utility level, and so on. Let me reiterate one more time that utility numbers are essentially our own invention. We assign utility numbers to bundles to represent the consumer's preferences. Okay, so it does not need to be the case that the consumer, in some sense, has a utility function inside their head which they maximize when they make decisions. Rather, if they are rational, if they have complete and transitive preferences so that they are able to put bundles of goods in order of preference, then they behave as if they maximize a utility function. Okay, simply by choosing the most preferred bundle of goods, they are choosing the bundle which maximizes the utility function which we have constructed to represent their preferences. Okay, so while a psychologist might say a consumer chooses a bundle because it gives him higher utility, in economics it's really better to say the consumer chooses a bundle, and because that's his most preferred bundle, we will assign that bundle the highest utility. Okay, it's a very small difference, but it's just recognizing the idea that preferences are real. This is what we imagine the consumer actually doing. And utility numbers are our own invention so that we can analyze consumer preferences using more powerful techniques. An idea that will become important as we progress is the notion of willingness to substitute between goods. Suppose that a consumer expresses the following indifference. They are indifferent between a bundle that contains 4 apples and 1 banana and another bundle that contains 2 apples and 2 bananas. Now here you can see the consumer is happy in some sense to reduce the amount of apples by 2, moving from 4 to 2, provided he gets an additional banana. This suggests some kind of exchange rate based on the consumer's preferences. Okay, now everybody is different, everybody has different preferences, so this exchange rate may well differ between people. We give this exchange rate, a subjective exchange rate, a name. We call it the marginal rate of substitution, which will denote MRS, marginal rate of substitution, which is the maximum amount of one good a consumer will trade for 1 unit of another good. Graphically, we can think of this as the slope of an indifference curve at a particular point. Okay, so the slope of an indifference curve is telling us how fast or the rate of change between one good and another whilst maintaining a constant level of utility, whilst remaining indifferent. So we could denote this MRS is equal to the derivative of Q2 with respect to Q1, and then we put this vertical line, which is a way of attaching notes to our derivative. And here I've just written du equals 0, which means utility doesn't change. Okay, so this is the change in good 2 over the change in good 1 under the condition that utility is not changing, which means I'm on an indifference curve. This slope of an indifference curve at a particular point tells us the rate of exchange, which is the marginal rate of substitution. Looking at this diagram here, we typically draw these convex-shaped indifference curves. This is the shape we will presume in most cases as we progress. Now notice at point F, the indifference curve is very steep. This means the marginal rate of substitution is a very negative note. It's large, it's very negative. Okay, if we compare that to point G, the bundle G, the indifference curve is very flat there. And you can see the tangency, the dotted line, which denotes the marginal rate of substitution. The slope of that tangent at that point is the marginal rate of substitution. It's still negative, but it's certainly less negative. So whereas at bundle F, the marginal rate of substitution looks like maybe -4, at bundle G, the marginal rate of substitution appears to be, say, -0.5. Now, we call this diminishing marginal rate of substitution. Okay, so whenever an indifference curve is convex, it exhibits the property of diminishing marginal rate of substitution. The slope of the indifference curve becomes flatter as Q1 increases. Remember that although we use the term diminishing marginal rate of substitution, we have to keep in mind that marginal rate of substitution is a negative number. So when I say marginal rate of substitution is diminishing, what I mean is it's becoming less and less negative. Okay, it's becoming closer to 0. Clearly, at point F, bundle F, where I suggested the marginal rate of substitution might be perhaps -4, and at G, MRS might be, for instance, -0.5. Now, we know -0.5 is a greater number than -4, but in absolute terms, the -4 is the greater number. And that's what we mean when we say diminishing marginal rate of substitution. Let's have a look at how a marginal rate of substitution is related to the idea of a utility function. So let's suppose we're given a utility function which depends on the quantity of good 1 and the quantity of good 2. Okay? Now, how could we describe an indifference curve? Well, we could write something like the utility of Q1 or Q2 equals some constant. Okay, so this would be the formula for an indifference curve. Now, different indifference curves, you just use a different constant number here. Okay, so this is what's called an implicit function, in the following sense that if Q1 changes, then we need to change Q2. So we say Q2 is an implicit function of Q1. Now, in your calculus training, you'll learn how to differentiate such implicit functions to find. Remember, the slope of an indifference curve we're looking for is dq2 over dq1. Okay, so this is what we're looking for. And if we have this equation, we could use what's called the implicit function theorem to find that slope. Let me just kind of show you one way of doing the same, which is essentially the implicit function theorem, but I'll write the proof in an intuitive way. So an alternative definition for an indifference curve could be the following. I could say change in utility equals 0. Okay, so this would be an equation that holds along any indifference curve. Along an indifference curve, change in utility, or the differential of the utility function, must equal 0. So what is this term here? Well, there's something called a total differential. Now, I know this might be new, but it's quite simple and intuitive. So let's learn it in context. The total differential is the following. How does this utility function change? Well, it changes because good 1 changes. So there might be a change in good 1. Now, how does this change the utility? What's that rate of change? the partial derivative of the utility function with respect to Q1. So this, in a sense, is good 1's contribution to the change. Good 1 changes by some amount. This is the rate at which it changes the utility function. That's going to contribute to that overall change. And then we do the same for the second good. We say, well, the rate of change of utility when good 2 changes multiplied by how much good 2 actually changes. So this is the formula. This is called a total differential formula. It's essentially breaking down the total change in utility into the changes that come from each of the two goods, each of them multiplied by the rate at which those changes affect the utility. So it's a very intuitive formula. Okay. Now, if I rearrange this formula, remember, along an indifference curve, now this is not always equal to 0, but on an indifference curve, this is equal to 0. Okay. So along an indifference curve, this is equal to 0. So I can rearrange this to get dq2 over dq1. Okay. And this will be the derivative we're looking for. So this is a slightly, I've skipped a few steps perhaps in the proof, but this is how the proof would work. And then rearranging the rest of the terms, I would get minus. On the top, I would have the derivative with respect to good 1. So the derivative of utility function with respect to good 1 divided by the derivative of the utility function with respect to good 2. The partial derivative, apologies. Okay. Now we're going to give these terms, we're just going to denote them as U1 to denote the partial derivative of the utility function with respect to good 1. That's called the marginal utility of good 1, divided by the partial derivative of utility with respect to good 2, which will denote U with a 2 underneath, U subscript, 2 subscript. And this is the marginal utility of good 2. Okay, so our marginal rate of substitution, which is the slope of our indifference curve, okay, which we've found by using the formula change in utility equals 0. This marginal rate of substitution is equal to the negative of the ratio of the marginal utilities. So if I know the utility function, I can calculate each of these partial derivatives. I can calculate the negative ratio, and that tells me the marginal rate of substitution at any particular point. Now, it can be shown that if we were to use a different utility function, v, which also represented preferences, okay, then this would also equal minus v1 over v2. So perhaps we could try that as an exercise. So let's show that marginal rate of substitution, although we can express it in terms of utility numbers, so marginal rate of substitution is the negative of marginal utility of good 1 divided by marginal utility of good 2. Now, we know that if we found one utility function u, that there are many, many more utility functions, okay? Which is concerning because it makes it look like the marginal rate of substitution may in some sense depend on this utility function. So we want to show that that's not the case. Okay, so let's let v equal f of u. Okay, so v is going to be a function which takes the utility numbers u and transforms them, and we'll say f is strictly increasing. Okay, now because f is strictly increasing, we know that if u puts all the bundles in the appropriate order to represent preferences, then so does v. Okay, so v is also a utility function. So we want to show that marginal rate of substitution is also equal to minus the marginal utility of calculated using this utility function divided by the marginal utility of good 2 using this function. Okay, so let's calculate these partial derivatives. V1 is the partial derivative of V with respect to good 1. Okay, how do we do that? Well, we'll use the chain rule. So we'll say it's the derivative of f with respect to u multiplied by the partial derivative of u with respect to good 1. Okay, and V2 similarly will be the derivative of f with respect to u. So how does changing utility change this function f multiplied by the partial derivative of utility with respect to good 2. Okay, so now if we calculate the MRS using this function minus v1 over v2, we should get df du okay, with a minus sign here, divided by df du, the marginal utility of good 2. And you can see that this term here, this strictly increasing transformation, simply cancels out, and we're left with minus u1 over u2, being the same as minus v1 over v2 over v2. Okay? So there are many, many utility functions, and when you calculate the marginal rate of substitution, it doesn't matter which one you use. This is a relief because we also know that the marginal rate of substitution is the slope of an indifference curve, and that is defined entirely using preferences without this kind of artificial idea of a utility function. Let's do an example to calculate the marginal rate of substitution for a particular utility function. So the following utility function is very widely used, and it's called the Cobb-Douglas utility function, okay, which takes the form the utility of Q1 and Q2. So the utility of a bundle which contains Q1 units of good 1 and Q2 units of good 2 is equal to Q1 to some power alpha multiplied by Q2 to some power beta. Okay? So this is an example of a parametric utility function, and it's very, very widely used. Let's have a go at calculating the marginal rate of substitution for this particular utility function. Now, there's several ways we could do this. So the first method, let's label this method 1, is we could just directly calculate MRS is equal to minus U1 over U2, okay, these marginal utility terms. So let's calculate those terms. U1, which is, if we remember, the partial derivative of the utility function with respect to good 1, which means differentiate this utility function treating Q2 as a constant. So if we do that, we would get alpha Q1 to the power alpha minus 1 multiplied by Q2 to the power beta, which we treat as a constant. U2, the marginal utility of good 2, would be the partial derivative of this utility function treating good 1 as a constant. So if we did that, we'd get Q1 to the power alpha multiplied by beta Q2 to the power beta minus 1. Okay, so let's calculate MRS now. So marginal rate of substitution would be minus U1 over U2, which equals minus this term here, alpha Q1 to the power alpha minus 1 multiplied by Q2 to the power beta, all divided by this term here. So let's put this beta at the front. Beta times Q1 to the power alpha times Q2 to the power beta minus 1. Okay. Now I can cancel out some terms. So I've got alpha minus 1 copies of Q1 on the top and alpha copies on the bottom. So this would be minus alpha beta and a Q1 on the bottom. And here I've got beta copies of Q2 on the top and only beta minus 1 on the bottom, which leaves 1 copy of Q2 on the top. So the marginal rate of substitution here, I get a very simple formula. It's minus alpha divided by beta, which are those parameters which are unique to each individual. So different individuals may have different alphas and betas. Multiplied by this ratio Q2 over Q1. Okay, so that's one method of directly calculating marginal rate of substitution. Let me show you another. So method 2. Now remember, I could take a strictly increasing transformation of this function and calculate the marginal rate of substitution of that function, and I will still get the same answer. So perhaps we could check this. So let's let v be log of u, okay? The logarithm is a strictly increasing function, so I'm allowed to do this. Well then v of q1, q2 will equal the logarithm of this. So let's just use some of the rules of logs. It will be alpha times the log of q1 plus beta times the log of q2, okay? Now if I calculate the partial derivatives, calculate these marginal utilities. So the marginal utility of good 1 using the function v will be the partial derivative of this with respect to good 1. So I'm assuming good 2 is q2 is constant. So I get alpha divided by q1. Okay. Now this marginal utility is different to this marginal utility. So marginal utility doesn't mean very much. Okay, this is ordinal utility. And so a concept like marginal utility is really quite meaningless. V2 I could calculate as beta divided by Q2. Okay. And now if I calculate marginal rate of substitution minus V1 over V2, I get minus alpha divided by Q1 divided by beta over Q2, which is exactly the same. So even though the marginal utility terms were different, the marginal rate of substitution, the slope of the indifference curve, is exactly the same, even if we use a different utility. As long as it represents the same preferences, marginal rate of substitution will always be the same. Okay? Now let me show you a third way. These are perhaps the most efficient ways, but there is another way of calculating marginal rate of substitution. So let me show you one more. And in this method, we're just going to take the equation for an indifference curve. So if we remember, we had v of q1, q2. So we'll still work with this v function. It's a little simpler to work with. Was alpha log of q1 plus beta log of q2. Okay. Now, an indifference curve. We're looking for the slope of an indifference curve. Okay, so we're going to imagine marginal rate of substitution is dq2 over dq1, okay, provided that utility is not changing. So the slope of an indifference curve. Now, what's the formula for an indifference curve? We could just write alpha log of q1 plus beta log of q2 equals some constant c, okay? So all of the different Q1s and Q2s that make this equation hold, they constitute an indifference curve, okay? They all generate the same level of utility. There's different pairs of Q1 and Q2 that generate the same level of utility. So let's see if we can get this, find this, the slope of this. So if we get Q2 by itself, for instance, so log of Q2 is equal to, let me see, so we'd have c minus alpha log of q1 all divided by beta, okay? So q2 is, and let's call this f of q1, okay? I've just used f to denote this function of, once I know q1, well, I'll take logs of it, multiply it by alpha, deduct it from c, and divide by beta. And then q2 is, log of q2 is equal to this, so q2 is e to the f of q1. Okay? Now, if I differentiate q2 with respect to q1, how do we differentiate the exponential to some to the power of some function? So we would take the derivative df dq1 and then multiply it by e f of q1. Okay? So that's the rules of differentiating exponential functions. You could deduce this from the chain rule also. Now we know that this thing here is just q2. So this is df dq1 multiplied by q2. Okay? Now if I calculate this derivative, it's just the derivative of this with respect to q1. So I get minus alpha over beta q1 multiplied by q2, which is exactly the formula that we were after from our previous analysis. So that's another way. If I have a parametric utility function, I could set it equal to some constant, try and get q2 by itself. Now that's not always possible, but in this case it was possible. This is because this is what we call a separable utility function. So when I can do that, I could then apply some different rules of calculus to find that slope term and get the same answer. Okay, so once you understand what you're looking for, the slope of an indifference curve or the ratio of marginal utilities being the same thing, you can solve this problem in various ways. Let's have a look at marginal rate of substitution using some different utility functions that we will find in the textbook. So our first example is called perfect substitutes. So this is, for instance, something like Coke and Pepsi. I would be pretty happy to swap one can of Coke for one can of Pepsi, provided they both had zero sugar, I guess. I'd be perfectly happy to swap these because to me they taste the same. And that's a kind of typical example of substitutes. Now, for perfect substitutes, utility is a linear function. So the utility of the bundle which contains Q1 units of good 1 and Q2 units of good 2 is just I multiplied by Q1 plus J multiplied by Q2, where I and J are just some positive constants. If we look at the indifference curve here, for a linear function, clearly the slope of this is constant. We can calculate this very quickly as simply minus I divided by j. So that's a very simple example where the marginal rate of substitution is constant. Perfect substitutes have constant marginal rate of substitution. The kind of goods we looked at, we typically draw are what we would call imperfect substitutes, where we have diminishing marginal rates of substitution. To give another example, let's look at the case that is called perfect complements. Now, perfect complements are the types of goods that you absolutely have to buy together. So the example here is slices of pie per week and scoops of ice cream. This individual absolutely has to have a scoop of ice cream with each slice of pie. If they have more slices of pie for one scoop of ice cream, their utility is not changing. Okay? Also, if they have one scoop of ice cream, we can keep giving them more slices of pie and their utility does not change. They need both together. Okay, so if we look at points A, B, and C, there they have one slice of pie with one scoop of ice cream per week. 2 slices of pie and 2 scoops of ice cream per week is on a higher indifference curve. Okay. Also, 3 slices of pie per week with a scoop of ice cream is on a higher indifference curve as well. That's point C. But if we compare point A with points D and E, there they have 1 slice of pie and we add 2 scoops of ice cream or 3 scoops of ice cream. It makes no difference. The consumer wants a slice of pie for each scoop of ice cream. Okay, so kind of an extreme example to give you the idea of what perfect complements look like. The utility function for this case is that the utility for a bundle containing Q1 units of good 1 and Q2 units of good 2, I simply look at the smallest of the numbers. So I look at the minimum of Q1 and Q2, and that tells me precisely my utility for that particular bundle. This results in these kind of perfectly L-shaped indifference curves that are perfectly vertical when good 2 is greater than good 1, so in which case the slope is infinity, and perfectly horizontal when good 1 is greater than good 2, in which case the slope is 0. So for those two cases, when good 1 is less than good 2, the marginal rate of substitution, the slope of the indifference curve, is infinity. When good 1 is greater than good 2, the marginal rate of substitution is 0, as the indifference curve is perfectly flat. Now, at the particular point where Q1 equals Q2, this is what we call a kink. Okay, the slope of this indifference curve changes very, very quickly. It's not a smooth change, so we cannot calculate a derivative at that point. So we say the marginal rate of substitution is not defined at that point. Now that we've analysed how to model a consumer's preferences, and we know a lot about this, we know what preferences are, we know the basic assumptions of completeness, transitivity, and monotonicity. We know about indifference curves and the properties of these indifference curves, and we know about marginal rates of substitutions, and we know about utility representations. So we know an awful lot now about the preferences side of this problem. Recall the basic problem is, out of all of the things that they can afford, consumers will choose what they most prefer. We've analysed the what they most prefer part of that sentence a lot so far, but what about the things that they can afford? Okay, so next we're going to outline the model of what we mean when we say affordable. Let's remember the basic assumptions. For our purposes, we will imagine there are two perfectly divisible homogeneous goods, 1 and 2. There are fixed unit prices for each good, P1 and P2. Okay, so this is a simplifying assumption. It doesn't matter how many units of good 1 I buy, each of them costs the same and they all cost P1. It doesn't matter how many units of good 2 I buy, each of them cost the same, the price is P2. Okay, so fixed unit prices is something we will assume as a starting point. We will imagine the consumer has a fixed income. So this is an amount of money we'll denote capital Y. And this is what they have available to spend. We'll imagine that we're just talking about a single time period. There's really no point in saving or borrowing with a single time period. But of course, this extends quite easily to multiple time periods. But for now, just one period of time, one decision. And we'll assume that there's no transactions costs and goods are available and there's perfect information. Okay? So under these basic assumptions, we can derive something called the budget set. So let's go to paper and look at what budget sets and budget constraints are all about. Okay, so let's consider a bundle Q1, Q2. Now we assumed that there are fixed unit prices for each of these goods, P1 being the unit price of good 1 and P2 being the unit price of good 2. So, if a consumer wishes to purchase this bundle, we can denote the expenditure required for this bundle as follows. If I'm buying Q1 units of good 1 and each unit costs P1, then I multiply these together, P1 times Q1, to give the total expenditure on good 1. Similarly, the total expenditure on good 2 will be P2 multiplied by Q2. So we call this the expenditure. How much in cash or in money terms does this bundle cost the consumer. Now we can define what we mean by an affordable bundle. Okay, so affordable essentially means that the expenditure required for this bundle does not exceed the consumer's income. So the condition is this bundle Q1, Q2 is affordable if P1 times Q1 plus P2 times Q2 is less than or equal to, so it does not exceed, the consumer's income, capital Y. So this is what we mean by an affordable bundle now. Okay. Now this is just one bundle. We can denote the set of affordable bundles. So sometimes this is called the opportunity set. Opportunity set. In most economics texts, it's called the budget constraint. And this is, let's use set builder notation. So it's going to be a set which contains bundles that satisfy the rule these bundles are affordable. So P1 Q1 plus P2 times Q2 is less than or equal to Y. Okay? So this is a set with many bundles in it, and they all satisfy the rule that these bundles are affordable. We call this the budget constraint. This is the set of bundles which our consumer is going to make a choice over. We also need to be aware of the terminology, the budget line. Okay, now the budget line is part of this opportunity set, but it occurs where the consumer spends all of their income. Okay, so when the expenditure for these bundles on the budget line is precisely equal to the consumer's income. Okay, now we'll see why this is called the budget line. If we examine this equation a bit more, we can see it's a linear equation. So P1 times Q1 plus P2 times Q2 equal to Y. This is linear in Q1 and Q2. Now you may be used to seeing linear functions expressed as y equals mx plus c is how you first learn about linear functions, where m is the slope term and c is the intercept term. Now here, Q2 is the vertical, the y-axis, and Q1 is the horizontal x-axis. So if we rearrange this to get Q2 by itself, we'll see that Q2 is equal to y divided by P2 minus P1 divided by P2 and multiplied by Q1. So this equation is just another way of writing the budget line. And here you can see an intercept term, y divided by P2. And you can see this slope term, minus P1 over P2. Now this is given a name. This slope term minus P1 over P2 is called the marginal rate of transformation. It's the rate at which the consumer can exchange 1 unit of good 1 for a unit of good 2, or how many units of good 1 they have to give up in order to have 1 unit of good 2. Okay, so it's an exchange rate similar to a marginal rate of substitution, except this does not depend on preferences. This is determined by the market prices. Okay, now in most textbooks it's called marginal rate of exchange, or sometimes marginal rate of substitution in exchange. But this textbook calls it marginal rate of transformation, so we'll stick with that. So let's go ahead and produce a diagram of the opportunity set and indicate the budget line. So let's start with a horizontal axis on which we'll put good 1. So the amount of good 1 we just labelled Q1. So I have 0 here. And a vertical axis for good 2, Q2. And now let's remind ourselves of the budget line equation, P1 Q1 plus P2 Q2 equal to Y. Okay? Or the way we rearranged it, Q2 equal to Y over P2 minus P1 over P2 times by Q1. So if we want to draw this, you could just use the technique of saying, well, this is the intercept and this is the slope. There's a slightly easier way, in my opinion, which we just do the following thought exercise. You simply imagining spending all of your money only on one of the goods in turn. So if I imagine spending all of my money on good 1, then I'm going to take all of my income and I'm going to divide it by the price of good 1. Okay? Clearly, if each unit of good 1 costs P1 and I spend all of my money on good 1, this is how many units of good 1 I can purchase. Okay, so if I'm spending all my money on good 1, then I'm saying P1 times Q1 is equal to Y, in which case Q1 would be Y over P1. Okay? So that's if I'm spending all of my money on good 1. Similarly, if I spend all my money on good 2, I would get Y divided by P2. Now that I know 2 points on this line, and I know it's a straight line, I can simply collect these 2 points. And in doing so, I've produced a diagram of the budget line. Okay? Now that method of doing this is going to be very helpful because in future lectures we're going to be looking at what happens when the price of this good changes and the price of this good changes, or when income changes. So it's very useful to be able to draw this quite quickly. So for instance, if P1 was to increase, if the price of good 1 was to increase, I know that this point stays the same because P1 does not appear here, and I know that this point would move inwards. So the budget line would kind of pivot inwards. So examining the axis in this way is very useful for when we're analysing price changes and so on. Okay, so now on this line, we know the slope of this budget line is minus P1 over P2, which we called the marginal rate of transformation or the marginal rate of exchange. Now, underneath the budget line, this entire set down here, which I roughly shade in, this is what we call the opportunity set. Or if you prefer, the budget constraint. Now, if I pick a point A within the opportunity set, then I know that it is affordable. Here, it's below the budget line. So I know, for instance, that P1 times A1 plus P2 times A2 is strictly less than Y. Okay? So I can afford it and I have some money left over. If I pick a point, say B, which is on the budget line, then I know that P1 times B1 plus P2 times B2 is precisely equal to Y. So everywhere along this line, along the budget line, represents affordable bundles where I spend all of my money. If I pick a point up here, C, which is outside of the opportunity set, then I know that P1 times C1 plus P2 times C2, so the expenditure required in order to purchase this bundle C, is greater than the income that I actually have. Okay? So this diagram is a simple way of representing what is affordable for the consumer, bearing in mind that we're analysing the problem of choosing the most preferred and affordable bundle. So the consumer will be looking only within the opportunity set, including the budget line, to find the thing that they prefer the most. Now that we've developed the tools, utility functions, marginal rate of substitution, and the budget constraints and indifference curves and preference maps, we can now take the basic idea of the consumer's problem, choose the most preferred and affordable bundle, and we can now express this in several ways. We have a graphical way of expressing this problem. Choose the most affordable bundle becomes, in our diagrams, choose the bundle that is within the opportunity set, or on the budget line, and is on the highest indifference curve possible. That sentence includes lots of made-up terms that we've used, but we're expressing something that's equivalent to choose the most preferred and affordable bundle. Our graphical version is choose the bundle within the opportunity set on the indifference curve that's furthest from the origin. We can also restate the consumer's problem as a mathematical problem now. Rather than choose the most preferred affordable bundle, we can write solve the problem, maximize a utility function subject to an inequality constraint, which is the budget constraint. So we've got two different ways of expressing the very basic idea of the consumer's problem, and in the next lecture, we will look at solving the consumer's problem, by which I mean fully describing the solution to the consumer's problem and analysing the properties of that solution. So, I look forward to seeing you next time, and in the meantime, take care.